We left off last time talking about the algorithm for finding A inverse, so let's try it out. Let's try it out on a 2 by 2 matrix, even though we know, don't we? We know the inverse of a 2 by 2 matrix already. We have a formula for it, right? So let's just remind ourselves what, if this is A, what A inverse is equal to. So it's 1 over 5 times 7 minus 4 times 10. And then you switch the diagonals and negative the wings. So 7 and 5 get switched. And the wings are negative 4 and negative 10 after you switch the signs. And this is, what is this, negative 5? 35 minus 40. Negative 5 in the denominator, so let's go negative 7/5, positive 2, positive 4/5, and 1 negative. So that's the inverse, right? According to the theorem. Yeah.
Is there any kind of correlation between this, or what is the correlation between this and like when you're translating something from your, or is there like any, because it seems so like that formula is basically 1 over the determinant, and the determinant can impact your, if you're translating something from, passing through a machine from either 2 dimensions to 3 dimensions, or within the same position, but you're changing the function somehow. This feels like there's got to be some sort of connection there intuitively because you're using the same.
I'm not sure if there's a correlation. I have to think about that a little bit more. I don't see it immediately, if there is one. All right, let's try this new algorithm that we just ended on last time, and see if we're going to get the same results. And according to the algorithm, what we want to do is we want to begin with an augmented matrix where we have A, and then on the right of A would be the identity matrix. And then what we want to do is we want to do a bunch of elementary row operations, so that the first part of the matrix that used to be A becomes the identity. And then what's going to happen is that the resulting matrix on the other side, which used to be the identity, should be the inverse. So let's write this out. 5, 10, 4, 7. And you don't need to draw the dotted line, but I'll draw it for a little while. 1, 0, 0, 1 is your identity. So let's reduce. I don't know. I kind of want to make that 5 into a 1. So let's multiply the first row by 1/5. I got 1, 2, and then 1/5, 0. Starting off with a fraction already. And then let's try multiplying the first one by -4 and adding it to the second one. So -4 row 1 plus row 2. So that would make that into a 0, one of our goals. And then, what was it again? So this becomes -8 plus 7 is -1. And -4 over 5. And just 1, that didn't change. Okay. And then I want to make this into a positive, so I'll multiply the second row by -1. Remember, this is the reduced row echelon. So I have 1, 2, 1/5, 0, 0, 1, positive 4/5, and 1. Oops, negative 1. And then we need to wipe out this 2 as our last step. So I'll take the second row, multiply that by negative 2, add it to the first row. So the second row stays the same. The first element in the first row stays the same because there was a 0 there. And then the whole point of doing this is to make that second element in the first row a 0. So now let's figure out what happens here. This is negative 8 minus 1, negative 7/5. And then this is negative positive 2. Negative 2 times negative 1 is positive 2, and then we add it to 0, positive 2. Identity. Yep. So that's our inverse, which is what we got in the original algorithm. Yeah. One of you guys? No, the end is not an elementary matrix. No. Yeah. Well, we know that the A times A inverse is going to equal the identity, and we might also use it for solving AX equals B, where we would have the identity or the inverse of that. Yeah. You can't really test it from the beginning without actually going through the steps to see that this is going to happen. So if we just focus on the A matrix all the way through, all these matrices are row equivalent. So the A matrix is row equivalent to 1, 2, 4, 7, which is row equivalent to 1, 0, 0, 1. So all those are row equivalent. And I don't know if there's any quick way to look at it and say it's row equivalent unless we go through the steps. But then we'll also see the whole idea that this, if it is row equivalent, then we can find the inverse. Nate?
We know which means when we use our algorithm, it will be row equivalent. So one hypothesis would be, if you want to know if it's row equivalent to your identity matrix, calculate the determinant, and all you care about is whether you get 0. If it's non-zero, our algorithm will work, and we'll get it. If it is 0, then it's not going to be row reducible. And we know that works for the 2 by 2 because we've been told this inverse formula is, now whether or not it works for other matrices is a mystery, but for 2 by 2.
Okay. Brian? You might get a zero row, a whole row of zeros or something. Yeah. You should. Yeah, be better. Okay. Anything else? All right, let's do one more of these using this algorithm, doing a 3 by 3 matrix. This time we don't have a quick way of checking, so we're just going to assume that this is going to be correct at the end. Provided Chris catches all my mistakes. So let's start off with the AI augment augmented matrix. 1, minus 2, 1, 4, negative 7, 3, negative 2, 6, negative 4. What once you get comfortable with doing it by hand, it's relative. Which means on the test situation, if I asked you to show me all the steps to get the inverse matrix, you should be able to do it. And then you can use your calculators to check if you've done it correctly. All right. So the 1 is already in the first slot, which is good. So let's just do, I'm going to do a couple of steps on this one. Let's get rid of that 4 by multiplying the first row by negative 4 and adding it to row 2. So we have 1 minus 2, 1, 1, 0, 0. Now this is going to become 0. Positive 8 minus 7 is 1. Negative 4 plus 3 is negative 1. And then we have a negative 4 here. 1, 0. And then I'll do the next step in the same step. I'll do 2 steps in one. This is a negative 2, so I think I want to multiply the first row by positive 2, add it to the third row. So what do we have here? 2, it's negative 4 plus 6 is positive 2. 2 minus 4 is positive 2 again. And then 2, 0, 1. Okay, right so far? All right, now I want to get rid of this 2. I think that's multiplying the second row by negative 2 and then adding it to the third row. 1 minus 2, 0. 1, 0, 0. The second row doesn't change. 1, oops, this is a 0, 1, negative 1, minus 4, 1, 0. All right, here's where we get 0 for that, the 2 spot. And now it's negative, this is a 1. Oh, which one? Here or this one? At which step? This one right here? Or this one? The second 2 here? Are you looking at that one? I don't know. 2. Yeah, it should be a negative 2. All right, we need to catch these mistakes before we move on. All right, we're here now. So this used to be, I put 0 here, but it was supposed to be a 1. All right, we are doing negative 2 minus 2 is negative 4. Yeah, that would have given us a 0 there, which probably would have been bad. All right, negative 2 plus 2, that's 0. And then 0, 0, 1. Okay, let's get that third row cleaned up with a 1. 1 minus 2, 1, 1, 0, 0, 0, 1, negative 1, minus 4, 1, 0. Mistake? One, negative 1. Negative 4, yeah. Negative 2 times negative 4. Oh, I did it with the first row. Ah, crap. All right. I think we should use the computer already. All right, where are we? We are here. Yeah, because I took this number. Is this correct now, negative 4, just to be sure? This is a negative 2. Phew, man. All right. It will be. Okay. All right, let's try it again. So we're still at negative 4 here, negative 1/4, right? So 0, 0, 1, and that's our first diagonal figured out. And then divided by 4, negative 4, 10 over 4, 5 halves. Divided by 4, positive 1/2. And divided by 4, negative 1/4, negative 1/4. Now we got fractions. Okay. So now let's focus on this value over here, negative 1. We want to eliminate that from the third row. So I think we just add the third row to the second row. And then I'm going to leave the first row open because I think I'm going to do 2 steps here too. So this is 0, 1, 0. That gets rid of that. And then now we just add negative 5 halves minus 4. So 8, 5, 13, negative 13 halves. Add 3 halves. And then add negative 1/4. And then I'll do the same thing over here from row 3 to row 1. What am I going to do with row 3 to get rid of the row 1 over here? This one? This one. From here to that one. I think that's negative 1, right? So that we can get a 0 in that spot. So negative, so this is positive 5 halves. 5 halves plus 1, 7 halves. 1/2 negative. And then 1/4 negative. Negative 1/4 negative. Positive 1/4. Oof, one more. This is really annoying. All right, just one time. You guys have to do this one time on the quiz. And then you guys can do it. Yeah, there's a quiz on Monday. But it won't be on inverses. It'll be on just matrix multiplication and stuff. I hope not. Sometimes I pick out problems and fractions just pop up. I don't mean to. All right, one more step. We are going to multiply row 2 by positive 2 and then add it to row 1. So I'm going to start writing from the bottom. Because those are already done. then I know that this is going to be 1, 0, 0. So that's the easy part. Now I got to multiply 2 times these fractions and then add it to that. So 2, that's 26, negative 26 minus 7, negative 19 over 2 times 2, 5 over 2 is the answer. 5 halves, and then negative what? Wow. Yeah, let's check. Yeah. Of course not. Damn it. Oh, is there? Yeah. So that means it's not invertible. All right, we did something wrong. What? I made what? I don't think it works that way. All right, let me try Wolfram. Damn it. Where did we make our mistake? All right, find the mistake. I don't know. It's the pretend inverse. All right, let's see. Let's see. A sub 0. I don't know. I can't believe I'm going to waste my time on this. To try to find the mistake. We can. Wolfram and the Inspire CX CAS calculator, Jessica's. I think between the two of these machines, I would say that they're right and I'm wrong. Thank you. 1 minus 2, 1, 1, 0, 0. 4 minus 7, 3, 0, 1, 0. Minus 2, 6, negative 4. So I like using this because it's, did you find it? Negative 2. Yeah. Where? Here? This one? So this is the place?
Second row, third column, -1 times -2 is +2, and then adding that to -2 takes you to 0.
Oh, there it goes. Da, 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 da. No. So it turns out that if you get zeros on the left-hand side, you need identity on the left-hand side. If you get zeros on the left-hand side, then there's all kinds of stuff that's not going to be relevant anymore because you're not going to be able to find your inverse. So over here, you can stop and say no inverse, or like Wolfram said, A is singular. Boy, that was. Whose character? Yours? I'm already a character, so. Chris.
So, I guess a couple of questions. Geometrically speaking, what is the inverse of a vector or a group of vectors, and then having a vector be singular, like what would that mean geometrically?
So I think by geometrically, I don't know exactly what those vectors mean with a matrix, but from a geometric point of view, we can think about this as a linear transformation that changes one vector to another vector. So the inverse would just take it back to its original state. So let's say if you have a vector that shears some object, then you take that sheared object and then do the inverse to get it back to the original object. So that's one way to view the inverse.
So then, what does it mean for it not to have an inverse? Like you could actually like transform something and not be able to return it.
Yeah. So yeah, one of the transformations, linear transformations that we had was a projection onto a line. So onto something. So if you project that, it disappears. Yeah, if you flatten it, then you wouldn't know how to originally put it back because you don't have that inverse to get back. All right. So we'll have a quiz on Monday about just the regular matrix algebra from 2.1. And then I don't know if I'll give you a quiz on Wednesday or the following Monday on finding an inverse of something where you have to show all the steps. And then after that, then you don't have to do it by hand. Again, for a little while. Yeah, I might just do it on Wednesday just because it's just one problem probably. Okay. So beyond inverses, the whole idea of inverses, beyond just being able to solve for AX equals B by doing the inverse, there's a lot more theory that goes into inverses. And what happens is that any matrix can be categorized as something that has an inverse or something that does not have an inverse. So the world of all matrices has a disjoint category where it's either an inverse or it's not an inverse, and it can't be both. And so knowing if something's an inverse has like some valuable implications. And so they have this inverse matrix theorem, part 1, that lists, what's L? Is that 10, 12? That lists 12 equivalences. If you can say that something is invertible, then it also follows that it's all these other things, which means if it's not invertible, then none of these things hold. So this is an equivalence theorem that says all or nothing. And so your matrix is either in or out. So let's take a look at it. If it's invertible, then it's row equivalent to I sub n, the identity. We already kind of established that. If it's invertible, then A has n pivot position. This is an n by n matrix. It has to be a square matrix that we're looking at. Right. So n has n pivot positions. The equation ax equals 0 has only the trivial solution. That's true because of part C, right? The trivial solution is 0, 0, 0, which means there's no free variables. Does that come along later on? I guess no free variables is the same as having n pivot positions. The columns of A form a linearly independent set, which means if it's not invertible, then the columns of A are dependent, right? So the opposite also will hold for everything else that's opposite. Linear transformation is 1-to-1, and somewhere along the line it's onto also. So that whole projection thing that we talked about, oh, we didn't talk about 1-to-1 and onto, huh? All right, forget it. The columns of linear projection is 1-to-1. The equation ax and b has at least one solution. The columns span all of Rn. Right? If it's all linearly independent, there's n vectors. It's going to span all of Rn. Linear transformation is onto. And then, J and K are saying that C and D are just another name for inverses, which means you can multiply to the left or multiply to the right. So that's just kind of follows. And then the last one, it turns out that the transpose is also invertible. Okay, so this is the first part. As we learn more theory, like determinants, we can add on information about determinants here. Like another thing that you would add on here once we learn determinants is that the determinant of the matrix is not equal to 0. So if the determinant of the matrix is not equal to 0, then it's going to be invertible. That's going to be another thing that we can add on to this. We're going to talk about eigenvalues and eigenvectors, and so there'll be statements about eigenvalues and eigenvectors that would go here as well. So we'll look at this list later on, add on to it as we learn more theory on matrices. But for now, this is what we got. The other part that's in this section, which we're not really going to go over in too much detail, is information about transformations. Oh, these things are not typeset correctly. What's this? Oh, what's 1 and 2? I don't know what 1 and 2 is. Anyways, so if T is a linear transformation and A is a standard matrix for T, then T is invertible if and only if A is also invertible. So, sure. And then backwards. Okay. So if we're talking about transformations, then this is the whole idea of the inverse says that we transform it into something, and then we can always take it back to its original shape. And that's all it's really saying. I think that's all I want to say about that. Okay. So when we revisit transformations, which probably will be, is today Wednesday? Next week, then we'll dig more into this a little bit more with looking at inverses, and maybe we might be able to see some pictures as well. All right, we're going to move on to the next section. So this is just a couple of theorems in this section. I probably won't assign homework for this section. This is a 2-3, and so we're going to skip over to 2-4. I think it's 2-4. Is it 2-4? What's 2-4? Oh yeah, we're going to skip over that too. Let's go to 2-5. Are there determinants there? You're not going to be wishing that long. Section 2.5. All right, in this section, we're going to talk about breaking things apart. So matrix multiplication, we multiply a couple of matrices together. Matrix factorization, we try to take them apart. And sometimes when we're looking at a matrix, the matrix might be complicated or might be too complicated to deal with. It might be better to actually take it apart for a variety of reasons. There's 3 special kinds of factorizations we're going to do in this semester. This is the first one, LU factorization. The other one we'll get to, the other 2 we'll get to when we learn more about eigenvalues and eigenvectors. But for now, let's talk about this factorization. So factorization in general breaks a matrix up into a product, not a sum, but a product of 2 matrices. Kind of like, when you factor a number, you factor 14 to 2 times 7. It's the same kind of idea, except it's probably not that easy. Huh? So let's take a look at one particular factorization, and this is just kind of a motivation for why would people want to factor a matrix. The LU factorization is motivated by some stuff in economics, where you have AX equals B, some B vector, and then the same AX equal to another B vector, and then another AX equal to a different B vector. So what we want to do is we want to be able to solve for these different X values. Now, if we know the inverse, then it's just going to be the inverse. It's going to be easy to deal with. But a lot of times, figuring inverses out isn't so easy, right? We can vouch for that. So in some cases, it might be better to do a factorization where instead of A times X, you have LU, the L matrix and the U matrix, equal to X, or times X is equal to B, and then deal with it that way. What is LU? Let's get some definitions here. So the L stands for a lower unit triangular, and the U stands for an upper triangular. So a square matrix is called upper triangular if all entries below the main diagonal is 0. Now, give me an example of things that we've changed to make it into upper triangular. What's that process? If you just do a row echelon, right, not necessarily the reduced row echelon, but a regular row echelon form, that automatically gets you an upper triangular matrix, if we haven't noticed already. Zeros in the bottom. So that's an upper triangular matrix. Now, L is not just a lower triangular matrix, it's actually a lower unit triangular matrix, which means it's got zeros on top and the main stuff only exists down below, but the unit says that the diagonal has to all equal to 1. So the diagonals are equal to 1. That makes it a unit lower triangular. So an LU factorization factors your matrix into the upper triangular and the lower unit triangular matrix. All right? Cool. You should get an L and a U in your result. So let's take a look at the 2x2 example that we have over here, and let's see if we can make that into an LU decomposition. So this is invertible, right? So if we go through the process of row reducing, right? If we go through the process of row reducing, then we have the unit matrix. Oh, this is not a good example. All right. I don't want to change the 5. Let's leave the 5 alone. What do we need to do to make this bottom one a 0? Times 4 divided by 5. 4/5 R1 plus R2. Negative, right? So that would be 0, and this would be whatever it is. 10, 4, negative 4 plus 7, positive 3. Is that right? Eight. Negative 1. Well, let me make sure. 5 times 10 plus 7. Oh, it's 8. Yeah, negative 8. So it's negative 1. I got to practice my math. So that's already an upper triangular matrix. So this is your U vector, looks like. Or not vector, your U matrix. So the question is, what is L? What is L? So remember the elementary row matrices that we did? So we did an elementary row matrix. We did an elementary row operation here, right? So let's do this exact same elementary row operation to the identity. And what are we going to get? So if we imagine doing this to the identity, so your identity, and then let's do the minus 4/5 R1 plus R2 business. We're going to get 1, 0, and then we get this minus 4/5 1. right? You remember that? Now, did you also remember that when you do an elementary row operation, we have an elementary matrix associated with it. And if you apply that elementary matrix on that matrix that you're working on, that you're going to get whatever the result was. Right? What's A? If I want to solve for A here, let me check your inverse knowledge. What's A equal to? Don't say U divided by E1. Is it U times E to the negative 1? That's not correct either. What should it be? E to the negative 1 times U, right? Because it's happening on the right side. It's on the right side. Yeah, it's happening on the right side. So what we really want to do is multiply both sides by E1 inverse on the right. So I need to multiply this by E1 inverse on the right. On the left. I was using my right hand. Sorry. I was going this way with my right hand. On the left. Sorry about that. Apparently, I don't know my left and right either. So this is what we have. E1 inverse. According to what we talked about yesterday or last time, the inverse of an elementary matrix is an elementary matrix also, right? But the inverse of a row swap is the row swap itself. The inverse of a row, multiplying a row by a number, was multiplying it by the reciprocal. And then the inverse of adding a row to another row was some sort of subtracting thing. You guys are looking at me like what am I talking about? We did do this, right? I have proof right here, the notes. So elementary row operation of the third kind, where we multiply a row by a number and then add it to another row. It's the same thing, except we're multiplying by the opposite. Okay? So now that we have that idea, this is 1, 0, positive 4/5 and 1. So guess what? To lower triangular matrix, it has ones in the diagonal. So there you go. That is exactly your lower unit triangular. So it turns out that this is the L that we're looking for. Okay? Yes? Yes. The opposite is. Yeah, because it has to be the inverse of that. Yeah. Well, we'll find a more an easier way to do it. I mean, we still have to do the row reducing, but we just have to keep in mind what our steps were. And so for a 2x2, it's really easy because you only take one step to get rid of that. You only have one thing to get rid of to make 0. So there's really only one step. So for a 3x3, we'll have a few more steps, but we'll take a look at that in detail. You can, that's just the number. And then how do you factor? You can't. I guess no, you can't do that for a 1x1 matrix. And it's I suppose, yeah. All right, let me throw out some more theory, and then we'll do some more examples. This is probably going to be on the new page. Now, this isn't really a full application of this, but it's kind of telling you the use of it. So in this particular problem, they actually gave us the LU decomposition already. Okay, so we'll take that. We could figure out how they got that later on, but for right now, let's just say this is the LU decomposition. Now, to actually use this in an AX equals B scenario, where A would be given and B would be given, and then we're looking for X. What we need to do is we need to do this in a couple of steps. We need to figure out what Y is equal to. This is we need to figure out what Y is equal to, and then we need to figure out what X is going to be equal to. So what it says here is that in the AX equals B equation, A can be written as LU, and then you do some associative properties, and then you have L times UX is equal to B. And so now you temporarily set this into as Y, and then you have Ly equals B, where UX is equal to Y. That sounds really confusing. So UX is Y, which is an intermediate vector that you're going to find, and then that's going to help you find Lx when you do Lx equals B. Ly is equal to B. All right, let's give it a try. In this particular problem, we have A and B, and this is Lu. So we want Ly equals B, and then Ux equals Y. So let's figure out what Y is first. Or Ux equals Y. So we have, what are we going to figure out first? Oh, we have to figure out what Y is. So let's do our L. So 1, 0, 0, negative 1, 1, 0, 2, 0, 1 times Y that we don't know. Is equal to the B that we were given. Is this hard to solve for? If you do the matrix multiplication, you can kind of see that Y1 is equal to 2. So that's already done. Right? So Y1 is equal to 2. And then we have here minus Y1 plus Y2 is equal to negative 4. And we know that Y1 is equal to 2. So Y2 is equal to negative 2. Let's box these things. So 2Y1, is it Y2 equal to 2? Oh, okay. 2Y1 plus 0Y2 plus y3 is equal to 6. Let's see, we don't have y2, but we have y1. 2 times y1 plus y2 or y3 is equal to 6. So this is 4. 6 minus 4 is 2. Y3 is equal to 2. So the y vector is 2, negative 2, positive 2. And then now that can help us solve for the x, the u. So now u, x is equal to y, says that our u vector, 4, 3, minus 5, 0, minus 2, 2, 0, 0, 2, times what you're looking for is equal to what you just found, right? And then now this time we start with the bottom. Last time we started with the top. This one we start with the bottom. 2x3 is equal to 2. x3 is equal to 1. And then minus 2x2 plus 2x3 is equal to negative 2. So minus 2x2 plus 2 times 1 is equal to negative 2. Is that negative 4? Minus 2x2 equals negative 4. And then x2 is equal to positive 2. And then the last one, 4x1 plus 3x2 minus 5x3 is equal to positive 2. We got 4x1 plus 3x2 is equal to 2. x3 was equal to 1 equals 2. So 4x1, this is 2 minus 6 minus 1, 6 minus 5 is 1. So this is 3, or no, that's 1. And so x1 is equal to 1/4. Yeah. Well, yeah, I mean, we can find the inverse and then, is that what you mean? Oh, yeah, augment it and row reduce, yeah. But if you augment it and row reduce, it's basically row reduced already. You just 3, 5, 2, 0, minus 2, 2. It's kind of already solved for, and even the first one with the lower triangular, it's already solved for, except the zeros are on top instead of the bottom. And so we want to go through this to solve for those particular variables. Okay? Yeah. I don't know if that plays into anything yet. Times 2, yeah. Yeah, I'm not sure. Is it just 2 though? I'm not sure if it's just 2. They would. So I'm not quite sure if it'll just be a factor of 2 or a factor of, oh, then if you scale or multiply it. Yeah, maybe. All right, that's your example. Oh, I don't want to do that one. Oh yeah, here's the algorithm that we were working on. Let's try to do an LU factorization, another LU factorization. So this is this is typed up nicer. Oh, and the one we did was only for a 2 by 2 matrix, so this is for a more general matrix. So let's get this down as a general algorithm. The example that I gave before this one. So the algorithm talks about those elementary row matrices again. And then if you have more than one elementary row matrix, like beyond a 2 by 2 matrix that you're trying to find the LU decomposition for, then you're probably gonna, when you find the inverse, remember that the inverse of the product is a product of the inverses in reverse order. So that's also another important thing to remember. But we'll see in this special algorithm that we don't even have to think about it that way. If you just, I'll see if I can do this without too many complicated things. So the main thing to do is keep track of your row operations. So I'm gonna keep the 2 there. Normally, if I was just row reducing, I probably want to multiply the top row by negative by 1/2, but I'm not going to do that. So let's keep the top row. Remember that the only row operations we want is multiply a row by something and add it to another row. Okay, that's all we really need. And then now we have. I need to multiply the first row by negative 1/2 and add it to the second row. So if I multiply that, that would be 0. Multiply this by negative 1/2, that's going to be a positive 2, plus 5 is 7. Negative 1/2, that's negative 1. Negative 1 minus 4 is negative 5. Okay? In the same step, I will get rid of this 6, negative 6. I will multiply 2 by 3 to get positive 6, and then add that to row 3. So that makes that into a 0. Negative 14, and then 10. Okay? So I got one more step. I'll take that one more step. And that one more step is take row 2, multiply that by 2, add it to row 3. That's going to take your 7 to 14, subtract, and then you get your upper triangular matrix. So the first row stays the same, the second row stays the same, and then the third row brings that to 0. This is also 0. Why? I don't know. I'm not sure anymore. It's still an upper triangular, but what can we say about this now? It's singular. It's not invertible. No determinants yet. All right, but now we have the upper triangular matrix. Right. So get the lower unit triangular matrix. Wait. To get the lower unit triangular matrix, we know that the diagonal has to be 1s. And we know that anything above that would be 0s. So now there's 3 spots that we need to fill in. And so what are the 3 spots that we're going to fill in? So we want to look at the corresponding Oh, is that too dark? Green. All right, so we took negative 1/2, right, to get this. So the elementary row operation would have been 1, 0, 0, negative 1/2, 1, 0, 0, 0, 1. So the inverse of that is the same except the opposite sign, right? And that gives a positive 1/2 in this slot. The next operation that we did took this third slot over the third row, the first slot in the third row, and we multiplied that by -3 or by +3. So the inverse would be multiplying it by -3. And then the last one for this slot, we got rid of that by multiplying the second row by 2 and adding it to the third row. So we're going to multiply it by -2. That's the inverse. So this is your L matrix. Yeah. Yeah, you could still factor it. Okay. So this is your LU decomposition. So your A was equal to whatever it was equal to is equal to L the L that we found times the U that we got the row reduced. Okay, we should probably check that. So we have our vector 1, 0, 0, 1/2, 1, 0, -3, -2, 0, or 1. And we want to multiply that with 2, -4, 2, 0, 7, -5, and 0, 0, 0. It's a good thing that's highlighted now. Oh, we want to have this in matrix form so we can see it. Is that the original matrix? So 2, -4, 2, 1, 5, -4, 6, -6, so that's it. Okay, so it turns out that this factorization is unique. There's only one way to factor it this way. And remember that it doesn't involve any switches, row switches, and it does not involve any multiplying a row by a number, right? Because if you do that, then you lose the 1, 1, the unit for the lower triangular. And I think there's a few facts about this. So if a square matrix can be reduced in a row echelon form without using any row interchanges, then it has an LU factorization. If A is invertible, then LU, then L and U are unique. Oh, so it's not invertible in this case, so maybe it wasn't unique. An extension of the LU factorization is, there's a lot of times we've been talking about you can do this without switching two rows. If you absolutely need to switch 2 rows, then you need to introduce a permutation matrix, which is an elementary matrix that switches a couple of rows. And then that permutation matrix will go in front of the LU decomposition. So when would you need to do this? When would you need to do a row swap? When you have a row of 0, when your first element is row 0 in the first row, or that's up there. So if you absolutely need to do a row swap, then that's just another elementary matrix in the very beginning step that you would do. Okay, and that elementary matrix in most textbooks, in most cases, is called P, PT, P inverse. It's called P. The original matrix is P, but then the inverse of a row swap is itself. So P is equal to PT, which is equal to P inverse. The transpose. Right. Yeah, and you need to switch. All right, so section 2.1 is due on Sunday. I finally put it up there this Sunday, and you guys have a quiz on Monday on section 2.1. Okay. Hopefully by Monday. I haven't even looked at it. I will grade it this weekend, maybe. No.